Okay, I think I have the whole Zoom backward recording thing figured out, so hopefully don't have to do that anymore. If you missed the VHDL initial lecture, you're going to have a bit of a hard time. So go and look at the announcement that I sent out that links the videos. That will help you pick up on VHDL because we're going to use it a lot throughout. I'll be handing back the exam at the end of the class today. I posted the exam averages and the top, I think high score is what I posted. I also posted the image of the distribution for it. The average was high 80s, the high score was like 98. So overall, I'm very pleased. If you happen to do very poorly, as I mentioned before, it turns out it doesn't matter that much. Don't stress, because the two midterm exams are only worth 20% of your grade overall. So even if you get 50% on one of the exams, that's only 5% of the total grade that you've lost. So as long as you're turning in all the homework and all of the labs, if you're getting like 75% on the tests, you're doing pretty good, actually. So don't stress too much there. Anyways, so today we're going to give you a few more tools to use as a digital designer. Some of them are going to be VHDL specific tools, and then some of them are going to be new devices. So the first one that I want to talk about are the Assert report statements. And you've seen them if you've started running the tests for lab 5 of the VHDL, where it runs through and automatically is going to detect if your adder is working. Because if you have a 4-bit adder and you're adding 2 4-bit numbers together with a carry in, right, then you have 2 to the 9 different potential inputs. And that's a lot to check on your own. You can check samples, but maybe you're missing like an edge case is what we usually call them, where there's one scenario that it's going to fail. It usually works, but there's one situation where it doesn't. You don't really like those situations. So we design tests that use assert report. And what assert is saying is I am asserting that something is true. So I would say something like assert x equals 0. That's saying it should be 0. Remember, it's apostrophes because it's a single bit. Now, if it's not, then I want to report an error. So the basic way is to say report error. So you could say something like error bad sum. That's the example that it actually uses inside of the test bench that I've provided for you. And all that's saying is that, well, whatever test I ran, I was expecting a 0 to be on X. If I didn't get it, let's print to the TCL console that there was a bad sum. Now, this has some limitations, right? Because it doesn't necessarily tell you where that error is or what it was expecting. So we can actually design better test benches than that. And we can do it in kind of clever ways, because you can't really know what it was supposed to be without going and looking at your code, right? And if this is a variable or something like is set up in the test bench that I provided, then even your code isn't helpful, right? Because it's auto-generating some, I don't know, I'll call it alpha for now, some alpha that is saying, hey, you're supposed to be this on this iteration of the loop, but it's not, so there's an error. Where am I, right? So we want to do something like, well, let's do something intelligent and make our reporting better. And we can do that by inside of the report statement, we can say, what was the value that I had? And we're going to do that by just using, well, what's called an attribute. The signals that we're going to deal with, the data types that we have attributes, and they're accessed with an apostrophe. So if I have a signal called X, I put a little apostrophe and then write what attribute that I want. So in the case of the value, what I want is image. Now, be careful in that this works really well for bits, standard logic. It won't work for standard logic vectors. It does also work for integers. So we'll get to how do we do this with standard logic vectors in just a moment. But we can say instead of there, we're going to say if x is alpha, if x is supposed to be something, and I want to report it, then I can report, well, let's see, which one am I going to do first? Standard logic tick image. And then we're going to say what is the image we want? Well, we want x. And there we go. And now that's going to actually print for us the value. But if we want to know what it was supposed to be as well, right? If we happen to know that, we can then concatenate. I talked about concatenate last time, I think, or did I not get that to you guys? Okay, so concatenate is a nice operation. This is and or ampersand, right? The ampersand sign is just saying that if I say have a standard logic vector S that is equal to 0, 1, 0, 1, and I have T that is 1, 1. Well, then if I assign F to S ampersand T, then all that does is it concatenates them or sticks them together such that F is now T and S. Sticks them together.
So it starts with T. And
oh, sorry, S. I did good catch. S and T. So 0, 1, 0, 1, 1, 1. So that's all we're going to do is we're going to take the actual value and then concatenate that with another string that says something like, well, to say string, we use quotes. I'm going to put a comma right here at the very beginning of it because I'm going to have it say like this is going to be 0, comma, expected 1. So everything in the quotes is just letters, it's just string. And so now it's going to report this and say, well, I got a 0, I expected a 1. Right? That's all this does. This automates some of your testing. It's a really useful tool. We'll slowly build up our capabilities for doing this. And the next step is how do we deal with it if it's not just 1 bit? Because if it's only 1 bit, it's usually okay, right? We can usually just go look at that really quickly. But if we want to do something like assert, I'm going to use S for string on this case. And I'm going to say that, let's say that it's supposed to be that 0, 1, 0, 1. That's what we use for S, right? Yeah. Now I'm saying S is supposed to be this. Well, I need those because it's supposed to be a standard logic vector. And then I can report, well, I'd like to use this image property because it's already there for me, but it doesn't work on standard logic vectors. So now I'm going to introduce something else, which is type conversion, because it works on integers. It doesn't work on standard logic vectors. These are just different ways of storing the 1s and 0s, right? That's all the difference is between the integer and the standard logic vector. But it has a limited amount of capability of what it can do with the different types of data. So if I want to do something with an integer, then I can do is actually convert something to an integer. So I'm going to say integer tick image. So now I'm taking the image of an integer, and the operator is expecting an integer. But S is a standard logic vector, so I'm going to convert it to an integer. So the first thing that I have to do is say, let's convert to integer. Well, I would like to just say parentheses SS and turn SS, or not SSS. Sorry, my code is SS. Convert S to an integer. But it turns out the Vhdl is obnoxious, and we don't have a way of going directly from a standard logic vector, S, to integer. So we have to take one more step. And write unsigned. In this case, I don't write to unsigned, which this is one of those other quirks of Vhdl that's not super helpful. S. Okay, so now what's happening is first, at the very inside, I am converting S to an unsigned value. Then I'm converting that unsigned version of S to an integer. And then I'm converting that integer into a string. Now this is going to be a little bit odd because what it's going to do is it's not going to report 0101. It's going to actually report 5. So this report, if it's not this, it will say 5. I can then combine that with this idea and concatenate this and say something like and expected some value. And I can take it even further. And I could do the same kind of thing. So standard logic image and expected, and I could add this also standard logic to image of, I'm going to use R for the reference, whatever I knew it was supposed to be. So that way it's variable as well. I can do that with the standard logic vector. Now I can start automating my reports, my test benches. So if I want to run a lot of tests, this is how I do it. Yes.
So where does this go in your?
In the test bench. So this will be in the test bench. You'll have the architecture begin process. Oh, and there will be the beginning of the process. So just inside the process of the test bench. So just like with our other test benches, where we basically do some form like this, where we're process begin, and then inside of that we do stuff, right? Which is something like X gets assigned to 0, Y gets assigned to 1. Wait for some amount of time, right? Well, here, if I'm testing, say, a full ladder, and X, Y are my inputs, and Cn is 0. Well, now I would expect that I'm adding 0 plus 1 plus 0. So I could go look at my waveform and go down vertically, right? Because my waveform is going to show me what the inputs are at each given time. And I can look at what the outputs are. Hopefully my sum is 1 and my carry out is 0. So then I would just go ahead and write assert sum equals 1. Report assert sum is 1. Report, I could say error bad sum, right? If I was just writing this, but if I wanted to write kind of clever code, then I would go ahead and use this one. Standard logic image of S. And that would give me what it is, concatenated with the string I expected 1. These apostrophes are unnecessary, right? That they're inside of the string, so it's going to treat them as text. So it's just going to give me the one. It's just a formatting choice. And then I would wait. Right. Yes.
The SLI, I think I just missed it. Was that shorthand
For this.
standard logic? And so you
Standard
can't-
logic image. No, you can't just write that. You actually could write a little function that would allow you to do this, that you could do that. But no, it's just writing on the board takes a really long time if I start writing everything out. But yes, good question. Yeah, so SL tick I, this is shorthand for that whole statement.
So we gotta write out the whole.
You gotta write out the whole statement, which is much less painful on a computer than it is on a whiteboard. Okay. Now, the next thing that kind of needs explaining, right, as you move through the project, because I've given you a test bench, told you you can run it, change your signals, but if we want to understand what's happening, the next thing we need to know how to do are loops, because it uses a loop. So if you're new to programming and you aren't in, say, Dr. Gibbons 1400 and you're in this class and this is your first kind of technical class, what a loop does is it runs through some sort of process over and over again. Based on two very common ones are for loops and while loops. So you could conceptually have something where if you wanted to add a number to a bunch of times, you could have for, don't pay too much attention to the syntax yet, because I'm going to just be conceptualizing what a for loop is in case someone doesn't know yet. So if I wanted to say for, I'm going to use II. So this is a programming habit I picked up. Anytime I use what's a loop variable, I use double letters. II. Most of your programming classes are going to tell you to use for I. I like to use II to let me know that it's a loop variable. Doesn't really take much more typing, and it keeps your code clean. And let's say 0 to 99. Then we could add some number. Let's say A equals A plus 1. And loop. So what this is going to do conceptually is A is having the value A plus 1. So if A starts as 0, then each time you go from 0 to 99, it's going to add A plus 1. So it's going to go 0, 1, 2, 3, 4, and it's just going to count up until you've added it 100 times, right? Because 0 to 99, that's 100 iterations. That's what a for loop does. The while loop just uses a logical statement, a logical condition, which is something while something is true. So you could do it while A is less than 100, it would run. While A less than 100 same concept. Going to do the same thing. It's just going to sit and add 1 to A until A is 100. And once it reaches 100, it will stop. That's loops. Of course, there's much more to them. We can do lots of things. We can use II inside of this. So if we wanted to index something, so if I wanted to build a list of numbers, for example, so I had a huge standard logic vector that was 0 to 100, or sorry, 0 to 99, then I could say something like that vector at the index II is A. This II is going to increment up every single time that the loop runs. It will access the index of that vector and put A into it. So this is going to end up with a vector of values Well, the first, if this is starting at 0, the first time it's going to be 1. So 1, 2, 3, 4, 99. Right? It's just going to stick those values in at these indexes of V. That's loops. They're not too complicated. But I just wanted to make sure that everybody understands what they are before I start talking about them specifically for VHDL. Now, I actually taught junior high for a while in the area, and I taught programming, and it was actually just required part of the curriculum to learn for loops and while loops. So I kind of hope that most of you have had some exposure to them. If not, and they end up causing you problems, come talk to me. Go Google. YouTube has tons of resources, right, for this kind of thing. Programming is really common. There's lots of resources for you out there. I'm going to talk about it specifically for how do we do loops in VHDL? Well, the first thing that I need to say about it is they're really only useful for test benches. We don't use loops in our code. When we're writing a source, a design source, we don't use for loops. And it's because they're not smart the way that they work in VHDL. They end up creating a whole bunch of extra logic in order to make it work. And it takes up a ton of resources on your FPGA. It's not desirable. So we come up with cleverer ways to do things generally when we're iterating through in digital design. But for test benches, they're incredibly useful, right? Because it's easy to write a for loop. So the for loops look something, well, very similar to the generic one that I wrote up. Here I'm going to use JJ, right? The loop variable doesn't really matter. It's just something that keeps track of where I am in 0 to 9 loop. And then I say end.
This is the correct syntax.
This is the correct syntax. One of the weird things with VHDL is that optionally you can give the loop a name. You don't have to, but you can name the loop. Sorry, I don't do this very often, and it's not in my notes, but I think it's like, I would say something like loop 1. It's now named loop 1.
So could you do that? Would you do that just to like explain where errors are to like
Yes.
get back?
Yeah, you would do that. What he has to ask is why would we use it is to keep track of where the errors happen, right? Because if an error happens in this loop, it'll actually say error in loop 1. However, it doesn't add that much functionality because it also will say line 60 whatever. If this is line 67. One of the issues is a lot of times in your TCL console errors, if you have an error somewhere down here, say this is a big loop and this is like 72, and there's an error here, the reported error in the TCL console will often report the loop as its error, so then you have to go look in. So hunting down where the error actually comes from is something of an art with VHDL and most programming languages. So just keep that in mind as you go through. I mentioned constants before in the lab, but I think it's worth mentioning again since a lot of you haven't used it. So constants are also another useful test bench item, and it's actually they're used all over the place, right? We're going to use them in the project upcoming. We just do it in the same location that we would declare signals. So say we're in a design source somewhere. Architecture and its begin will be down here. Right, so after the architecture, before its begin, is where we declare things exist. So like signals, so I could have a internal signal carry is a standard logic. Now I have a signal that's carry. Well, I can do the same thing. Constant, give it a name, X. It's going to be a standard logic vector, again, shorthand. The difference is a constant, I have to give an initial value, which We do that by putting colon equals. And if I want the X to be 128. There we go. Now, anytime I write X, I'm getting a standard logic vector. Well, I actually couldn't use 128 because that would have to be an integer. I would have to do, I don't know what number this is, but something like that. Now, if I use X, I'm getting a standard logic vector there. I could, if I wanted that 128 constant, I'm just going to call it end, is an integer that is equal to 128. So now, if I went down here and I was inside of my design and I was not doing good design and I wanted to use a for loop for I in 0 to end loop. Now it's going to go from 0 to index, whatever that happens to be, which in this case is 128. That's how we use constants, is it helps us make our code easier to read and easier to modify. Okay, sorry. I think that's all we need to really understand that test bench that I've designed for Lab 5, and it will give you the groundwork that you need based off of the provided Lab 5 test bench and this a little bit of additional material. Hopefully you'll be able to start trying to build test benches for the upcoming Project 1. So Project 1, we're hopefully going to start today, right? So hopefully we're finishing up Lab 5. I hope that most of you have started testing your, what are we at? We're a 4-bit adder, right? For Lab 5. We need to finish that one before you move on to Project 1. It's okay. We actually have 2 weeks to do Project 1 this week and next week. The nice thing with Project 1 is initially I was going to have you design a slightly more complex ALU than I have in the past, right? ALU being arithmetic logic unit. And I talked about that last lecture. So what I've done, I've actually changed my mind, and I'm going to have you design one that's basically the same as I've done in years past. Then later, when we start integrating our ALU into a calculator, right? That's going to be our final project, is we're going to build an ALU, and then we're going to build it up slowly until the final project is a calculator. We're just going to build parts of it at a time. I'm going to have you build one ALU, and then I'm going to provide you with the correct ALU to use later, because the one that we're going to use is actually more complicated, for one, so I'm going to save you some of that work. And for two, the provided ALU will mean that you will all be using the same brain essentially within your code, so your errors are going to be more similar, so you'll be able to work with each other better. Rather than having different ALUs that have different architectures and different problems, you'll have the same ALU and the same problems, hopefully. So we'll design one ALU, then I'll give you a different one to use for a later project, well, for the final project. So the ALU into project I talked about last time. And fortunately for us, we don't really need to know any more material. If you understand Lab 5, it turns out that Project 1 is not that difficult. As long as you remember a concatenate symbol, right? We're going to have to concatenate something because this is the schematic symbol for an ALU. It's going to have input ports A, B, and it's going to have a couple different modules. One of them is an adder that has no carry on it, and one of them is an adder that considers the carry, meaning the carry in. So one of them has ports A, B, C in, but C in just is ground. And the other one is A, B, C in, and C in's going to come in here. So all right, it's gonna look something like this, right? A couple of internal blocks. We've already designed the adders, or at least we'll have, they're gonna be 8-bit adders. So A is going to be 8 bits, B is going to be 8 bits. If I add two 8-bit numbers together, how many bits is my output? 9 bits. So that means this is going to be 9 bits. That means my output, which we're going to call R, is going to be 9 bits. One of these blocks is going to be an XOR. Okay. What that means is it's going to XOR A and B. But A XOR B, well, if I do this with a 4-bit example, and I XOR these two, well, exclusive OR is this is not true, this is true, this is not, that is, right? It's 4 bits. The inputs are 4 bits, the output is 4 bits. So that means the output of this is 8 bits because I'm XORing A and B. I'm getting 8 bits. They're going to stay the same size. So the 9th bit is going to come from the carry in, actually. And so what we're going to say is if the output of this XOR is F, it's going to look something like CN ampersand A XOR B. Yes, thank you. Now it's 9 bits, right? Because I have an 8-bit result concatenated with a 1-bit. That's what we're going to do. The other two operations are load and hold, and they're really easy. You'll read the lab and figure out what they do. Project and lab description, same thing. Okay. The difficulty in the project, main takeaway is basically you're going to build multiple components, wire them up together like the picture I just drew and done, right? The hardest part of this is not the modules, it's connecting them together correctly. I talked about when else statements last time, right? For the mux. No? I swear I did. You guys are crazy. All right. So when we build a mux with 4 inputs, let's say, not 6, let's do 6. This would be really annoying to build in code using like a truth table, right? The standard design process that we've thought about so far. Because if there are 6 choices, I0, I1, I2, 3, I4, I5, then what that's saying is my M output needs to choose one of 6, right? And it's going to look at this select signal, but that select signal can't be just 1 bit because it has to be able to choose 6 different options. And 6 is 3 bits, right? Because 2 to the 3 is 8. 2 to the 2 is 4. 6 options doesn't fit in 4. I need to go to the next size up. That means it's going to have 2 options that aren't used, which is okay, but I need at least 3 bits. So that makes my select signal 3 bits. Well, the way I write this, rather than doing a truth table, because that would be a nightmare, right? Because I would have a 3-bit select signal and 6 inputs. And if these are suddenly 8-bit inputs with an 8-bit output, right? Now it becomes a bit of a nightmare. You could never do that truth table. It becomes impossible, right? So we need a different way of designing it. Turns out it's really, really easy in Vhdl because the program will take care of it for us as long as we follow the right syntax, which is to say we're going to say M is I0 when we're going to call this signal just S. And so on. So what it's saying is M, the output, is I0 when S is 0, 0, 0. Otherwise, I1 when S is 0, 0, 1. Until you get down to, it's assigned to I5 when S equals 0, 0, 1, 1, 0. I mean, we actually don't even have to go in order. If I really wanted, I could just say 1, 1, 1, as long as whatever was controlling my mux knew what it was supposed to be, which is really nice if I use a constant, right? I can declare a constant that would use 1, 1, 1. So if I was up here, I had declared a constant, C, I think C is a good letter in this case, constant C of standard logic vector size 3 or 2 down to 0, and its value is 1, 1, 1. Then instead of saying S equals 1, 1, 1, I just say when S equals C. Right? Benefits of constants. Then I would say else. Here, let's say that M is 8 bits, right? So that means I5, all those are 8 bits. I'm going to do an else and say something like that. X is a fine character for standard logics to be. It usually means dual driven, but here it's just saying my output should be X's if I give it a bad input. If a mux is selecting something that it's not supposed to, do X's. This is helpful if you actually don't connect the select signal. That way, when I have select is U or undefined, my output is X. And now I know, oh, I connected my select wrong. It's a really good tool to try and identify what's happened. Yeah.
So would this go in the architecture section or the
This
process?
This is inside the architecture, and this is combinational, so it doesn't need a process.
Okay.
Yeah, so we're going to run into some issues later on where there's one way to do this inside of combinational logic, which is everything we've done so far. Everything we've done is combinational, which is to say the output depends only on the combination of its inputs. Later, we'll design logic inside of a process, not just the test bench. We'll actually design things inside of a process, and that will be sequential logic that will depend both on the inputs and the previous outputs. It has memory, right? Sequential is, so sequential says this, then this, then this. This one is all of this happens at once. It's a mux, it's combination. So yeah, so this would be right after the architectures begin. For example, if I build this mux. And that's all this is. This is a mux, that code. There is an implied, right? Because this else is taking care of the 2 other options. I have 6 options, but there are 2 others. It's basically done this for me. Connected these other 2 out and connected it to X. That's what it's done. Now, there are other kinds of devices, right? Other combinational devices. So next week, we're actually going to start into sequential devices. We're going to start learning devices with memory. For today, we're going to hopefully wrap up the remaining combinational devices because they're not that complicated. These are chapters, some combination of chapters 9, 10, and 11. I would strongly suggest just going and reading in chapter 9, especially if you're having a hard time with the VHDL. Is chapter 9, it's kind of, I'm pretty sure chapter 9 is that introduction to VHDL, and it will describe a lot of this to you in a different way than the lectures and labs have. So if you want a different perspective on it, it's a good chapter to read. Chapter 11 or 10 rather wants us to go talk about something called encoders. And encoders are used all over the place. And all encoders do is they're a way of taking inputs and encoding them in a different way. How do we want to store that data, right? So let's say that I have something that is a decimal input. 0, 1, 2, 3, 4, 5, 6, 7 is fine. And I want to encode it as binary. Right, this is basically what we've done. Well, I have 8 options. I need 3 bits. This is 0, 0, 0. 0, 0, 0. I have a hard time doing this when I do it this way, actually. 0, 1, 1, 1, 0. Right, that's binary. Well, there's something else that we call binary coded decimals. What BCD is, it's a way of representing numbers where we directly want to represent our 10 possible decimal digits. So that if I want to write the number well, I used 128 earlier, so 128. Well, we could convert this to binary, right? We know how to do that. We did on the exam. I think like 2 people missed the question. So most of us know how to do this without errors. And I don't think anyone missed all of them, so good job. And I think most of the ones that do miss probably just hurried, but this 128, it's an easy number, right? It's 1 bigger than 127. So we go, this is 9 bits, and there's a 1 in the biggest bit spot. However, binary coded decimal is represented different, which is to say that each of these decimal points is represented by 4 binary bits, because that's how many it takes, right? So this is 0, 0, 0, 1, 0, 0, 1, 0, and then 8, right? Just for a refresher, if you want to remember how to do this, we have 4 bits. They're 1, 2, 4, and 8 valued. And we can start with this, well, 8, right?
So how do they not take more than 4 bits? Wait, never mind, sorry.
Oh.
You're right.
For those that don't know, you figured it out. Those don't know, because there's 10 different options. 2 to the 4 is 16. 16 can contain the 10 different options. However, as you just realized, there are extra. This is a little bit wasteful, but it turns out to be an easy way to represent decimal. If I were, say, designing like a counter that wanted to display these. Well, then I could come over here. It's the same thing, right? Here, it's the same as this column, which is the zeros, until you get down to 8, then it's 1, 0, 0, 0, 1, 0, 0, 1. The rest of those are thrown out. Sorry, the bottom rows for those that can't see is 1000, 1001, basically 1, 0, 0, 0, 1, 0, 0, 0, 1. And that represents the 8 and 9. That 8, 9 would be, unless I did something wrong, which I don't think I did. That's how we would encode binary coded decimal. It's just one way of storing numbers. It's just a different way. And we could then go ahead and start designing like converters, right? It's just a truth table. I could have some inputs, take some output, and design digital logic that transforms it. There's another kind of encoding that is really popular in older electronics and still happens all the time. I don't teach it in depth because when it happens, it's behind the scenes and you're not aware. But you do need to know that your computer is going to be doing this a lot. And the encoding is called one hot encoding. Well, all one hot encoding is saying is that if I have the decimal number, 0, 1, 2, 3, and I want the one hot, then what it does is my 0th option is, well, if I have 4 options, I actually need 4 bits. 2, 3, 4. That's one hot encoding. Is it's just saying whatever my selection is where the 1 is. Right? So the 3rd digit is a 1, that means I got a 3. I'm not going to have you do much with this in terms of design or anything. This is just a concept that you're going to need to understand what it is, because later you might see some errors inside of your TCL console that reference this. Yeah.
Would the first one not just be all zeros?
No, because it always wants one hot.
You said 3rd digit on like
Oh, sorry, the 3rd.
3.
I'm 0 indexing, so 4 is the 3rd index. Sorry. The longer I go in the semester, the better I am at always 0 indexing. So its index is index 0, 1, 2, 3. Yes.
What would 4?
4, I would have to actually add another 0 in front of all of those.
So it kind of just looks like an identity matrix.
It is. And there's this kind of implication if I wanted to convert between one hot and binary, I can do that, right? I could build a one hot encoder, and it would be really annoying to do it with this many, but with the 4 options. So let's say I had one hot and I wanted to convert to decimal. Well, these are my inputs and my out, or sorry, not decimal, binary. And my decimals are 2, 3, 4, 0, 0, 1, 0, 1. Right. And then I could start designing logic that would do this. Noting that these are my inputs, and then each of the columns of the binary are an output. Right? Because a truth table only outputs 1 bit per circuit. So we would design one circuit for each of those columns. Now, if I go to 4, you couldn't do that, right? Because I had never taught you 5 input K-maps. That'd be really hard. So if we ignore the 4, erase that, well, now we've got a K-map with 4 inputs, essentially, and we could go and start figuring it out. We just convert it. You guys already dealt with a different kind of encoding, right? On the exam. I gave you the truth table to encode binary to 7-segment display. Right? And that says, well, if this is signal A, B, C, D, E, F, and G, well, each one of those is an output with an input corresponding to some decimal number. That's all that question was. It was an encoder. It was, how do we encode binary into 7-segment display? Decoders go the other way. Decoders take something that is encoded and pull it out. Over here, very common encoding scheme is gray code. If I want to represent things as gray code, I would come over here. Over here is gray, 0, 0, 1, 0, 1, 1, right? Because it's changing every bit, and then it's 0, 1, 0, and then 1 1 0, 1 1 1, 1 0 1, 1 0 0. Yep. Now that wraps back around, right? Because this and that are only differing by 1 bit. They're logically adjacent. We could do our K-map with these as our inputs. Each one of these zeros is an output. We have 3 circuits. We've built ourselves a binary to gray code encoder. Um,
What use?
what use is gray code? Good question. So gray code is nice because of the logic adjacency. Is it adds a lot of stability when less signals are changing if you're counting through. There are, well, let me do it this way. There's many reasons to use it. One of them is actually very tactile. So I was designing a circuit once upon a time that was a MUX that had each channel, rather than being digital signal, was analog, right? We've talked about the difference between analog and digital. The analog signal would pass through if I chose it. And what the analog signal was actually coming out of a rat's brain. It was a neural recording device. It had 100-something electrodes in its brain, and you want to go measure what each of those electrodes is seeing, right? So you're going to multiplex through and sample this one, now that one, now this one, and go look at it. Well, I wanted to do it fast because I wanted what's called high temporal resolution. I wanted to do it fast. Well, there's an issue where because digital signals do that, right? They step. They draw a lot of current during this change. So we get this really high spiking transient current. If when I did the initial design, if this was 0 0 0 and this was 1 1 1, when I would step through all those channels and get to 1 1 1 and switch back around, every single one would flip. And in this case, you know, I need something like 8 of them, and they're all toggling at the same time. So I get this big transient current and actually ruins the measurements. Whereas if I gray coded it and I selected it that way, I only ever had one changing and my currents were never large. In fact, it was always the same level of current and very predictable. That's one real world application of why you would use gray coding. So don't kill the rat. Well, so I can measure the signal. That's what I wasn't going to kill it. It was just rat brain signals are really small, even compared to small digital signals. So I needed to minimize the extra noise, is usually what we call it. Okay. Did I oversimplify this? Like, because this seems really simple to me. Am I wrong? Was this confusing in any way, the encoders? If you get confused, chapter 10.2, we'll talk about encoders at length. A lot of this I generally feel like is really hard to deal with until you've built something out of it, until you have a reason for it, or you have homework to do in it, right? And there is a homework posted to do some VHDL writing, so make sure you do that. Okay, there's only one more device that I want to talk about before I start handing out the exams. And these ones are really important. They're called shifters. A shifter is going to, and this is going to be a little bit interesting because there's a couple different ways of implementing it. You can implement shifters with memory or shifters without memory, meaning you can either build them as combinational devices or you can build them as sequential devices. Either way, the function is the same, okay? So let's say I have a standard logic vector of 0, 1, 1, 0. What a shifter does is I can shift left or shift right. So if I want to shift left logical, LL, SLL, this will make more sense later, but this is how we reference it in VHDL. The SLL would transform, well, it shifts here to 1, 1, 0. Then the question is, what happens here? And we can actually get to choose. We can design whatever is easiest. We can shift in. Zeros is very common. It's not this 0, it's just a 0. So if I kept shifting, again, I would get that. The 1 goes away. If I don't want that to happen, if I want to move it around, then I would use what's called a barrel shifter, an end around barrel shifter, which is just, it rotates through. And so instead of doing this, well, I'm not going to draw it. It just, this 1 would come back around, the end around barrel shifter. Now, these have a ton of uses. They're all over the place. One obvious one for end around barrel shifter, if I'm going through, is a pattern generator. Let's say I wanted to generate a pattern. I could just stick it into an end around barrel shifter, and I would look at one of those. Like I would come in and peek here, and it would shift through and spin around. The other one that we use a lot in digital systems, if you take that from me, is for a queue. Let's say you have something that is acquiring data, right? Saving data that's coming in, saving signals, and you have something that is analyzing the data. Well, let's say the analysis takes longer than the acquisition. You have a shift register, which is what we'll deal with later. So shifter, if I say shifter, it usually means it's a combinational device. If I say shift register, it's the same thing, but it's sequential. It has memory. And what they do is, let's say I was measuring something. Well, the first one would come in and it would get measured. And let's say then I went and measured the next one, it would shift this over and got a 0. And I would take the next measurement and say that was a 0 as well, and I get 1, 0, 0. And then I get the next one, say it was a 1, this one shift over, this 0 shifts, and I get a 1. It's just a queue. It's another reason we would use shifters. Now, the implementation of shifters is not something that you're ever going to have to build on a breadboard, but understanding them can be helpful, especially if I have you do the homework. Actually, we're a little low on time, so maybe I'll have you do that homework. Yeah, I'll just have you do that as homework, because it's not that difficult if you just go look at the book when it points it out to you. In fact, I'm going to write, oh, that's funny. Forgot that was in there. Yeah, so that's shifters. We'll get to using them. I want you to be aware that they exist as I kind of talk about them and build up some more sophisticated terminology. But that, the encoders, shifters, adders, muxes, those are kind of our advanced combinational devices that are of most importance. So if you understand those, at least what they're doing, you don't have to design them overall. Hopefully you could design like this gray code encoder, go from binary to gray. I hope that you could do that. But that's about the level of complexity for there that I would need. Okay, let me grab the exams. Last name?
Dawson.
Josh. Joshua. Last name?
Record.
Jaden? Last name?
Easy.
Parker, right? Riker?
Yeah. Nice. I know. That worked out good.
I was just looking at the last name and. There we go. What's funny is these guys. Last name. There.
Sorry.
That I missed some of the maps. Here.
Oh,
Why is that one? There's a one.
yeah, fine, I can- Sure. I'm not sure. But definitely on this one, you needed to do
Most
the
of them
four.
are just like rushed into the
Why?
water.
I still.
Yeah.
So you have most circles, but the thing you have to realize first, is you need to get the biggest box possible.
Oh, I do.
Even if you overlap, like you really have to, you need to get the biggest box possible.
Okay. Did the
That's the thing you have to do.
some products. And then I half my skills.
I think it's because you didn't say what it was. Just say what the odds most devices. It's an excellent.
Oh.
So you have the truth table for I just didn't have, he didn't write. No, so he didn't know that he knew what it was. He was just like, he thought,
Okay,
he
yeah.
didn't realize.
That.
So that actually really sucks, that one right there.
Yeah.
Because I think, yeah, the truth table right. So.
How'd you do?
I don't know how y'all might test it. Never knew there was so many people in this class.
Haven't turned around yet.
Never.
So do you guys have to take those 4 CS classes for electrical engineering? It's just interesting. Advisors.
So
advice.
fun statistics, 20% of you don't know what a chihuahua is. Or at least don't know what chihuahua reads as, which is
No, I
fine.
didn't.
So I got everything from ranges of gremlins to question marks, which was pretty fun.
Did I get my test?
Oh, did I miss you? Oh, you were out. What was your last name?
Dodge.
Oh, I was gonna use yours. Yours is a really good example.
Oh, you can use,
Congratulations.
you can use my example.
No, it's okay. I just like having someone that got a lot right, but
Grab one.
Mine looks like a gremlin.
you weren't the only gremlin. I want you to know that. I don't know what
Oh.
inspired it, but
I mean, what's really the difference?
right.
There isn't one.
So I will say the most points missed on this exam came from question number 15, where a lot of you overly aggressively applied stimulus to A, B, or A, C, and D, right? You only needed to change B once. Everything else was wasted effort, right? That's the point of testing for hazards. And guess what? I gave you the simplest possible version because it didn't matter if you went from 0 to 1 or 1 to 0. Either one generated a hazard with this XOR gate. So if you did the simulation right, it shouldn't have taken very much time. Weirdly, most of you that didn't understand the priming the circuit and how to stimulate to find a hazard, also did the gate timing wrong, which was very odd. If you don't understand the timing diagrams, you may want to talk to me or like get some sample problems or work through it, check the homework, something, because they're really important. They're going to stay very important going forward. And they're worth a lot of points. And I want you all to get them right because they're a nightmare to grade, if I'm honest, because once you get it wrong, once you get one wrong, I have to go through every single line, right? Because if the last one is right, you probably got them all right. And grading that is easy. Lots of mistakes are hard to grade. So that one accounted for most of the mistakes, most of the errors. You guys did really well on, I guess, which would be question 7 overall. I was very happy with that. Right, that one was just the straightforward timing diagram. We weren't looking for hazards. I provided the stimulus for A, B, and C, or X, Y, and Z in this case. And then we were just supposed to monitor what happened at the output. Some of you did not read the instructions on that one, in that I said, you may consider the gates as ideal, parentheses, no delays. Several of you added delays. You worked too hard at that one. Part A on that, I think everybody got right. So good job, at least on that. The K-maps, the most common problem there was in, so number 5A, a lot of you didn't catch that there were the 4 corners that you could use to simplify further than using just a 2 input. So that would have been a minor error. And then on problem 6, it was much more common. The issue was you failed to flip the not bars as you're supposed to with the product of sums. That was the most common problem. Other than those issues, those common issues, the points were kind of missed all over the place, which was kind of a relief when I got to the end and actually started tallying the scores. Because the way that I do it is I grade every single exam 1 page at a time, just so I'm on the same thing. And when I was first doing it, I was like, this is the worst exam I've ever seen because there were so many different problems that people were missing. It turned out that none, like overall, you guys actually did really well. It was just very different issues, which is a really good sign, actually. This is a really good sign. I'm very happy with the way, the understanding that I've seen out of you all. It's gone better than my last semesters. I usually end up having to curve a little bit, and this I didn't. The average, I think I ended up posting was like 88. Was that what it ended up being?
Maybe 78. I don't know.
Let me pull it up. I got 3 minutes. Oh, it's lower than I thought. Yeah, sorry. The overall average was 83, which what that means is at the end of the semester, well, I'll look at the total exam scores. And you may end up actually getting like a 2-point bump on this one, depending how things go. I'm not going to put it in yet because people would much prefer to see their grade go up later, right? It's nice and happy surprise. So be aware, the average was a little lower than I thought it was in my head, so we may end up bumping. The odd one was the distribution was much wider. I usually get either a tight clumping or what we call bimodal, which is to say there's a group that doesn't do very well and a group that does very well and not very many people in the middle. This one was just kind of a long-tailed normal distribution, which I realize that you guys haven't taken statistics yet, so it just looks like this, right? I posted that plot, which is to say most of you got around this 85-ish mark, and then a few of you did much better, and then it kind of slowly tailed off. Most of these problems are going to pop up again, this kind of idea. You're going to see K-maps again on the next exam. You're going to see timing diagrams. You're going to see a hazard. If not on the next exam, then at least on the final. So these are things to prepare for. The 2 exams together, the 2 midterms are 20% of your grade. So even if you did poorly this time, it's not the end of the world. The final, I think, is also 20% of your grade, and it's going to be cumulative. And that means I'm going to pull some of the most important stuff from this exam and the next exam to put on the final. So just going forward, be aware that this material isn't going to magically disappear if you ignore it. I hope that you take the time to kind of learn and refresh and understand so that you can do better as we go along. I do have 1 minute. There's something that is important to understand with this degree that is really difficult in that in this area, they don't tend to hire people with very low GPAs. So the program is broken into this major. If you haven't talked to an advisor, you might not know this. This program is broken into 2 parts. There's the pre-professional program, which you are all in right now, and there's a professional program. So the professional program is the junior and senior level classes. And in order to get in, you have to apply. Don't worry, it's not competitive admission. It's literally, you have to have a 2.8 to get in. The reason is, in order to graduate, you need a 2.5. And it turns out your engineering courses get harder as you go along, not easier. And so we make sure that you start at a 2.8 so you can fall off a little bit as you go through. If you make it through and graduate, you will probably find a job. But you do need to plan for that and make sure that you're doing well and understanding the material, because as often as it will feel like at times that these classes are disjointed material, it turns out that they all build on each other, and I want you all to succeed. And so that means understanding and learning good study habits. So if you didn't know how to prepare for this exam, come talk to me. If there's something you didn't understand, come talk to me. I want to help you all succeed, but I can't do that unless I know you're having a problem, and there is an army of you. There's many of you, so I have to work with you. You need to reach out, and we can figure out how to keep you on track and successful. Anyways, that's all for my time. Come talk to me on office hours if you need to talk about the exam. I'll hang out here for a little while, but have a good day.